Alright guys, last one. We've got a storm. Okay, this is question 13. I should remember to say which question we're looking at. Question 13, paper 4-1, summer 2017, 0654 again. Okay, we've got a storm here. Okay, and we're being asked, why can we see the lightning before we hear the thunder? Well, the idea there is that lightning is seen via light waves. They travel incredibly quickly. Thunder is carried by sound waves, which travel very quickly, 340 meters per second, but nowhere near as fast as our light waves. In fact, if you look at those numbers, yeah, if you think of us as maybe 3 times 10 to the 8 and 3 times 10 to the 2, right? We've got a ratio there of 3 times 10 to the 8 over 3 times 10 to the 2, really, right? Not exactly, but it'll do. So we've got 10 to the 8 over 10 to the 2, 10 to the 6. All right, so our light wave is traveling 10 to the power of 6, 1,000,000 times faster than our sound wave. Okay, so the time it takes should be 1,000,000 times bigger, 1,000,000 times smaller for the light, and 1,000,000 times bigger for the sound. That sound is still very fast, however, it's nowhere near as fast as our light. We've then got this picture here. We've got negative charges up here and positive charges up here, and we've been told that we're building up an electric field. Electric field is a region of space. This is very important. Okay, it's an area where a charge experiences a force. Now what you could add there is a charge experience an electric force. Okay, the whole idea is if I put a charge in this field, then it will start to move one or two in one direction or the other. Okay, because it will experience a force. If I put a neutral thing in here, it won't move because there's no force, there's no charge. Similarly, gravitational fields are regions where mass experiences a force, and magnetic fields are regions where magnetic materials or magnetic poles experience a force too. Okay, we're asked to calculate a current, and we're told a charge and a time. Okay, so this is an equation that hasn't come up that often in these past papers. It might come up a bit more. Okay, Q equal to IT. Quit is my way of remembering that. Okay, obviously without the U in there. Okay, Q equal to IT, and therefore I is Q over T. And this is a classic example of Cambridge choosing its numbers very wisely, because when you look at these initially, they are quite weird numbers. 1.21 divided by 0.00011. Well, when you divide them out, you realize that 11 squared is 121. So actually, there's a factor of an 11 coming out. You end up with a nice 11,000 amps. 11,000 amps, all right? This should be telling you why we don't want to get electrocuted, because there are 11,000 amps going through our body. Sorry, we don't want to be hit by lightning because we're having 11,000 amps going through our bodies. Okay, that seems pretty scary to me. All right, last one, and I've not done it yet because a few people have said they want to see how to do it. All right, this is an example of, this is an unfinished diagram. Okay, you notice here that we've got our object and we've got the focal point, and now crucially our object is further away from the lens than the focal point. Okay, so what we're expecting here is to produce a real image. How does that work? Well, we need to draw 3 lines. Okay, complete the radii diagram to show the 3 rays of light, not 2 but 3. You notice they've drawn the top one. This top one, what it does, it passes through to the middle, and then it passes through the focal length on the other side. Focal point, sorry, on the other side. This one here, okay, we just carry it through. Okay, the middle line just passes straight through. The bottom line does exactly the same as on the top, but in reverse. So this guy's going flat then bent, this guy's going bent then flat. Okay, I've done that very, very quickly, but really the idea here is a parallel line up here, passing through the focus here, passing through the focus here. Notice they do the opposite, the top and the bottom line here. Okay, now these 3 lines should meet. Why do they meet? Because that is where our image is formed. Okay, we're asked to draw an arrow, and they've handily told us it should be upside down to show where the image is formed. I like to write a little eye there as well, just to show that eye is there. Okay, now I think the bit that people were having trouble with was what would happen then if we were inside the focal length. Well, if we're inside the focal length, okay, it's going to get messy, but I thought I'd show you it anyway. Okay, let's just imagine we placed our object inside the focal length, the rules would be the same. Okay, so actually this line wouldn't change. Okay. The middle line would change because we have to always pass through the center. Okay. Now we've got a problem because we're inside here, my third line I can't do. Alright, because I have to pass that third line through here. But remember, actually, we only need 2 lines to do this. What you should find is that those lines on the other side aren't going to meet at any point soon. Okay, these 2 lines here, sorry, aren't going to meet any point soon. So what we do is say, okay, well, they're not going to meet. I'm just going to extend them out. This is where I told you it's going to get really, really messy. Okay, I'm just going to extend these guys out, or what we say, extrapolate them out on the other side. Okay, and what you should be able to see then is that actually my lines meet way over here. Okay, so we've got 2 situations here. We've got my object on the left hand side of the focus, alright, on this left hand side, and then I've got the object on the right hand side. When we're on the left hand side of the focus, we get an image over here, and this is what we call a real image. Yeah, over here this is a virtual image. Alright, there's no light coming out here, but what actually happens is when this thing hits my eyes think that the light has come from over here, and we see something which is bigger. And the case here, really, that's what we are doing when we're using a magnifying glass. Alright, we're placing something inside the focal length of this thing, and therefore causing a virtual image, causing that light to look like it has come from over there, when actually it hasn't.